introduction, and thank you everyone for coming. So this work was done in collaboration with Franck Tarpin-Bernard and Bertrand Rivet in University Grenoble-Alpes at the Engineering Human-Computer Interaction Group when I was still a PhD candidate, and now I'm with Nataliya. So, brain-computer interfaces or mind control. We have all been dreaming about this for ages. Here is just one of the examples of the cover of the comics of Wonder Woman of 1942, when she can control her plane with the help of her diadem. Well, we are in 2016, and bad news, we are not here yet. Actually, not at all. Because it's quite complicated to get things to work from the brain. First, because the brain signals are attenuated and noisy. Actually, what we are getting is not a signal itself. It's more an average of millions and millions of neurons firing from the brain. This is like something what we are getting. It looks like this, and we need to deal with this very noisy data. So today, the technology is still reserved for people with disabilities that cannot have any other means of communicating. Something like people with locked-in syndrome, yes-no communication. So before going into the details of the talk, let's see quickly how does it work. So I'm going to talk about brain-computer interfaces that relieve from electroencephalography, or EEG. First, we need to acquire the brain signals from the brain. Usually we put something like the headset on the head of a person. There could be a lot of them, different models, different quality signals. We need to do some signal processing on these signals to extract the features of our interest. Then we need to classify these features to build the models of what we call humans' thoughts, so that our user can later on use these signals as commands in the applications. There are quite a few BCI paradigms. That is, what can we actually capture? For example, we can have... Oh, something is wrong. Do you hear me? Yeah, it's okay? I think it disappeared, but okay. So we can have something like a monitoring of the mental state of the user. For example, if a person is stressed, depressive, we can get some insights about this information. Or what we can do, and this is called passive BCIs, what we can do is we can introduce some external stimuli into the environment of the user. For example, a lead that will have some frequencies, it will be flickering, and the person can look at it, and it will evoke some particular brain signals. This is something we call reactive brain-computer interface. And finally, when a user is performing some voluntary control, like for example, he or she imagines actions, for example, left or right hand movements, this is what we call active brain-computer interface. And this is a focus of our work here. Otherwise, there are two types of BCIs. Either we have a synchronous BCI, that is when first a system is given a cue to a user. So we cannot start using the system just right away. We wait for a cue from a system, and then we start imagining our, let's say, hand movements. Otherwise, there is an asynchronous type of BCIs, that is where a user is free to perform whatever action at whatever moment of time he or she desires. Of course, this is interesting because whatever interface we are using, brain-computer interface or any other interface, it's usually much more of interest to have asynchronous interaction. What is very important with brain-computer interfaces is that today they all need training. We cannot just put a headset on a head of a person and then hope that we will discover something. No, we will find out nothing until the signals will not be recorded to train the classifier to recognize the particular patterns from the brain of this particular user. It's something like a fingerprints. We need the samples. No sample, no functional system. Here is one of the examples from the state-of-the-art systems to train a user to push a cube. I did this screenshot on purpose because I'm pretty sure not all of you even see the cube. It is somewhere there deeply. And, well, push the cube. I guess you have a lot of ideas how we can push a cube. Is it with 2 hands? With 1 hand? Should we imagine it like really pushing? Should we imagine actually cube and the hands and the action? How should we imagine the action? Well, nothing of this is indicated on this screenshot to train this particular action. So it could be quite complicated for a person to understand how we actually will perform this action. So there are quite a few limitations of the training brain-computer interfaces. It takes time. It takes around 10 to 20 minutes for 2 actions. Let's say we want to train the system to recognize an imagined hand movement, left hand movement, and right hand movement. Well, it will take around 10 minutes to do it. And moreover, well, if we are not even sure and we cannot give the precise insights to a user how she or he needs to perform this action, we can actually demotivate the user. Usually what happens is they come super motivated because we say we're going to do some mind control there, but we just need to do some training beforehand, and then we lose them because they're demotivated, because they don't understand what's happening. Is it them who are doing it? Is it the system? So let's try to make the training BCIs more suitable, especially more suitable for human-computer interaction applications. We got some inspirational. For example, from the state-of-the-art works where we try to shorten the training process. There is a possibility, for example, to capture when a brain is perceiving an error. There is a very specific signal called error potential. Some people, what they're doing, they're taking this signal and they are sending it as a negative example to a classifier, to say classifier that this is a bad example. So we can suppress the signal and train the system with new data. But there is no explicit implication of a user. It's still happening on implicit level. Or what we usually do is that we can bias our users. Like we can give some positive feedback, even if it is they were not performing that good. We can say it was fantastically good, so we keep them motivated doing the task. These 2 insights make us think about something that is happening between a professor and a student at school or at the university. A professor is giving us some new information that we didn't know. This kind of a system is giving us a result of the classification about our performance, mental performance. And then a student tries to understand this information and hopefully ask questions if he or she doesn't understand it. So what if we will have this option in our system? Meaning, what if we will give a possibility to a user to give a feedback to a system about the classification result, if he or she understands it, if he or she is okay with it or not. So we will basically having system feedback and user feedback. That is our co-learning for brain-computer interfaces. A user will give a feedback to a system. And instead of having some long co-learning phase, some very long training where we don't know what's happening, how it's happening, a user will be involved actively. And actually the system will not function if the user will not be involved. So here's this classical BCI loop I just presented you in the beginning. So the training, the acquisition, the classification, signal processing, and we are adding 3 new steps here. So a possibility to give from a user to give a feedback to a system. We adapt this feedback and we can do the incremental learning. So how does it work? What we are having here, we are having a system that is based on one single trial classification. That is, we have the signals divided in 1 second epochs with an overlap of 250 milliseconds. And then we are applying some signal processing. That is a bound pass filter to preserve the frequencies we are only interested in. And that's what we are doing. We are applying an independent component analysis. More precisely, its version that is called fast independent component analysis. Why? Because it's a blend separation technique that unmixes the signal. It's constituting maximally independent components. So what we are having afterwards, we are having our averaged epoch and we are having our reference epoch. And we are comparing them to look for the distances between both of them. And the one that has least distance will be the classification output. So instead of our 10 minutes training, the system is fully operational in 1 minute. Okay, it's good. We have our system, it's fast. But how are we going to present all these quite potentially heavy signal processing issues like distance measures, classification output to a user? We don't want to overcharge a user with information he or she doesn't need, and the chance that a user will actually understand the signal processing is not that high. So how about to get some inspiration for the visualization of these distance features from something that is not from the brain-computer interfaces, but actually from interactive machine learning? For example, a work of Franck and Hall that is a general method that proposes discretizing the attributes in the feature space, like we can see here. So it allows to obtain a separation of the features in the rectangular regions. Or, for example, the work of Rivet and colleagues of 2005, where they try to project the whole feature space in 2D space. And they try to preserve the distances as close as possible. And finally, the work of Seifert and colleagues of 2009 that is proposing actually a very elegant way. What they do, they project all the classes in a circle, and each class is presented in the form of the rectangular. And we can see the distribution of the points. They belong to each of them to the class. The problem with this approach, the distances are not really preserved. So we got inspiration from all these 3 works that are not used in BCIs, and we are proposing to have a Wachspress coordinate projection. So we are having here 3 classes, let's say a wolf, a rabbit, and a white square. So it is a triangle. The big white point is the classification output. Little points are the distance features that are presented. It could be, of course, generalizable to other, if we have more classes, let's say we add a car or something else. It could be a square, a pentagon, etc. So we are having here a system feedback that is a visualization part. And user feedback here is a possibility for user to change this. So he or she, without knowing the details about what are distance measures and features, can change, has a button that is called distance, and it will change the computational distance that will apply to the algorithm. So he will have the points that are behaving differently. It's not different really in the different sense, it's just as a distance. So the classification result is preserved, but what we are saying to a user that the algorithm is completely new, so it can potentially work. And what is happening that it works. They do believe it's another algorithm where they change it, and it actually performs better. They can always add more trials if they want, because the system is automated with 1 single trial, and etc. So we validated this. We tried to validate this protocol within a little game, Little Red Riding Hood, where there are a wolf and a rabbit, because our hero is a Little Red Riding Hood, and he or she needs to get to the house, but there is a wolf and a rabbit. If our user hears a bunny, a rabbit that is jumping, he or she needs to select a bunny, and if it is selected, the werewolf will be gone. If the user hears a werewolf, it means he needs to select a werewolf, and the werewolf will be dead. Good werewolf is a dead one. If there is a mis-selection, then the bunny is dead, and a user cannot move towards the house. For the selection here, we used a brain-computer interface paradigm called motor imagery. That is, users should imagine hands to select a wolf and feet to select a bunny, because this is related to the noises the animals are doing. We have validated this within 4 groups. One group in green shows that all of there were both possibility of having user feedback and a system feedback, so users could play with the system. Red means that there was no feedback at all. Yellow means there was either no visualization or no possibility to users to give a feedback. I cannot present you all of the results, as it is a Tokai paper, just one of them very briefly, that is comparing to the baseline. There is a significant a positive change in the classification accuracy, almost 10%. As for the systems that are not having either system or user feedback, then there is a problem with the classification. It's almost random. So as to conclude, to the long and tedious training problem, we proposed a column architecture for BCIs that is operational in 1 minute. For the feedback representations that are poor, we proposed a minimization technique. And for the usability of BCIs and law, stay with me for my next talk. Thank you for your attention.
Thank you very much for the talk. Mike Shakerman, University of Waterloo. You presented, or you stated that your system is operational in like 1 minute as compared to maybe 10 or 20 minutes when you compare it to other systems. And you brought up the example of being able to distinguish between maybe right or left hand, or maybe a hand and a foot. Is that not really a function of how distinct these two actions are that you want to be able to distinguish? Like right and left arm might be very different, whereas maybe pinky and thumb of the same hand would be much harder to distinguish between.
Yes, in any case, it depends. What I recommend with this system, as it is single trial, there is no hope that it will start distinguishing, like, you know, at 60 or 70% of classification accuracy. If you really want to go in the details of, there are quite a few papers, so we really need to choose carefully what we want to ask for distinguish. For example, it was proven, there are quite a few papers saying that for the foot, to distinguish between a left and right foot, this is like very complicated task. It's much easier to distinguish between feet and hands, so that when I recommend to use my system, I usually try to give the guidelines that to use something that was already proven by the state-of-the-art works, that it is distinguishable. Moreover, if it is proven that it is distinguishable within single trial systems. Notably, the case of hands and feet, it is the case. Between two hands, it is also the case. Feet, it's trickier. Fingers, it was also proven that it's possible with the EEG. I don't remember that I have seen the papers with the single trial. Always possible to try, but I would prefer to use more trials with the system because it's always possible.
Great. Now we'll work on dynamically using the visualization and training. My question is on, because ICA is kind of based in your solution, have you noticed any changes when you have lower number of electrodes? And if so, how would you go about addressing that issue?
Sorry, can you repeat again your question?
Basically, the number of electrodes, and would that impact your approach with training?
Okay,
yeah.
Thank you. It really, once again, really depends on the paradigm what we are using. But if you're talking about ICA, no. I have tried it with several combinations. You can check it in the paper. We can discuss later. It's 16, 32, and 64. I don't see like really significant changes in this one.